So I think this is officially like take 3. We're gonna do it so good this time because now we've just had a bunch of practice. Deep breath. All right. Hi, welcome back. Welcome to my shop. Thank you for coming. If you're new here, my name is Jen. I'm a subscale flight test engineer, and I'm also the team captain for Offbeat Robotics, where we bring you the hijinks. I recently had the pleasure of visiting EMF Camp in East Nor, UK, and I was given the opportunity to talk on stage about steel from the molecule up. Unfortunately, due to some technical issues, my talk was cut a bit short, and I promised to put this video together because nerds love to nerd out. So first of all, let me thank the staff and volunteers at EMF Camp for having me out. It was a wonderful experience. I also want to thank especially the AV team who worked very hard to make a big unwieldy event go as smoothly as possible. If you came to see me early on that cold, rainy morning, thank you very much. This is for you. So without further ado, let's talk about steel. Combat robotics is one of many areas in which you will encounter steel. The ubiquity of steel is owed to our ability to alloy iron with other elements, combining their desirable properties to make new materials. So first things first, before we even talk about steel, we need to understand its primary constituent material, iron. So listen, if you have a PhD in material science, this may not be the talk for you. Unless you're here for the jokes, I do have jokes. But if you are very new to material science and material selection, then I have jammed information in here that I hope is valuable to you. Initially, I thought I would just talk about the steel that's on the robot, maybe the 4 kinds of steel, but I think there's a big difference between someone telling you which material to choose versus thinking through the process and then choosing those materials for yourself. And hey, by the end, maybe you'll be ready to tell me why 4140 steel is not good for drive shafts, or at least you'll be better prepared than the average internet commentator. So without further ado, let's talk about crystals. Okay, I'm being a little bit funny here, but the truth is everything that we value about steel is directly linked to the crystalline structures that iron, as an element, naturally forms. So dirt nerds, geologists, this part's for you. And yes, this whole thing is a pretense for me to show you my crystal collection. And no, the crystals do not have magical powers, but they do have interesting properties. So first up, we have calcite and selenite. These are both super common. Calcite is a carbonate mineral. Selenite is also called gypsum, and it is formed by calcium sulfate dihydrate. It makes a huge variety of crystal shapes and has some interesting industrial applications. Next is quartz. Quartz is everywhere. It's silicon dioxide, and it is the most common mineral on Earth, often used in jewelry making because it can come in a huge variety of colors when other elements get mixed in during formation. Glass is also silicon dioxide, but when it's melted and reformed, it does not have a natural crystal structure, so it's not considered a mineral. In that case, it is an amorphous solid. Carborundum looks really cool. It is full of color, like a bismuth. My sample will cut you if you hold it wrong, but in this particular crystal formation, it's actually quite brittle. And then diamond, the end of the Mohs scale of hardness, so shiny, very hard, actually a lot more common than De Beers would have you believe. And then we have anthracite. Now anthracite is the outlier here. It's coal, and although it follows the mineral name convention having ITE at the end, it's not a mineral, it's just a rock. It looks like a lustrous metal, but it's actually biomatter compressed under high pressure. Iron, however, is a lustrous, ductile, malleable, silver-gray metal. It's in group 8 on the periodic table, and it is known to exist in 3 or more allotropic forms. Allotropy, or allotropism, is the property that some chemical elements have that allows them to exist in 2 or more different forms in the same physical state. These are known as allotropes of those elements. Iron may have more than 4, but the conditions that would be required for the others to form won't easily happen on Earth, so I just don't really think about them. And the kind of crystal that iron forms depends on the conditions at the time of formation, which means with heat and pressure, we can push iron through different crystal phases. So the first allotrope of iron that we're interested in forms a body-centered cubic crystal lattice. She's giving body. At temperatures below 912 degrees Celsius, that's 1674 F, the F is for freedom. This is what you will commonly see in the wild. The body-centered cubic crystal structure of iron is also known as alpha iron, but we're going to call it ferrite. On this diagram, each of the black dots represents an atom of iron, and they're held in this shape by the bonds that are formed through the interaction of valence electrons. Do not skip class, kids. This molecule is thermodynamically stable, and it makes for a fairly soft metal. One critical aspect of the crystal structure is the slip plane. the direction in which the crystal is most likely to deform or will most easily deform. Another critical aspect is the rate of cooling. The rate of cooling from a molten liquid to a solid will determine the crystal size. The faster a liquid cools or crystallizes, the smaller the grain size will be. The longer the cooling process, the larger the grain size will be. In terms of hardness, material dependent, if you have a bunch of tiny crystals rapidly forming in the same sample, their individual orientations will vary. And you wind up with grains that are locked together with opposing slip planes. So if I push on a piece of steel from one direction, the grains inside will resist deformation because they're pushing against each other. In iron, the crystal lattice can be more easily seen in things like iron meteorite samples that cooled very, very slowly over a long period of time out in space. The lattice pattern here is large enough to be seen by the naked eye. In steel production here on Earth, the metal is cooled much faster, and the grain size is small enough that you will need a microscope to see individual grains. At higher temperatures, iron also forms a crystal that is face-centered cubic. She's giving face. This is sometimes called gamma iron, but we're going to call it austenite. This will be important in a couple of minutes. On the Mohs scale of hardness, which we use for minerals, not usually for alloys, iron only comes in at about a 4, 4.5. Meanwhile, diamond is a 10, just like me. Meaning, if I have a diamond in one hand and a piece of iron in the other, and I rub them together, the diamond will definitely scratch the iron. In fact, I have a small collection of diamond discs here in the shop that I use to cut and grind hardened steel. A diamond's crystal shape is called diamond cubic. How original. And as you can see, it's a much tighter arrangement of atoms. The reason why carbon is able to form so many molecular shapes is because each carbon atom has 4 valence electrons, so they can easily bond with other carbon atoms to form long chains or rings. A carbon atom can bond with another carbon atom 2 or 3 times to form double or triple covalent bonds between those carbon atoms. It's a very friendly element, free hugs for everyone. Now, because iron is soft, we can work it. We can heat it up and smash it into shapes, and it will hold those shapes when cool. What it will not do in its pure form is hold a strong edge. And as you can imagine, it's going to get scratched or deformed when it comes in contact with a harder material or a lot of force. Diamond, meanwhile, cannot be smashed into useful shapes. If you smack a diamond with a hammer, that diamond is going to shatter. It is very hard, but it's also very brittle, so it won't tolerate shocks and impacts. Many bonds make carbon strong, and carbon all on its own has some fantastic industrial applications, but carbon could never do for us what iron does. Okay, so we have iron, which has the useful properties of thermal stability, malleability, but it isn't very hard. And we have carbon, which has the useful properties of hardness, but it's brittle in its pure form. And I want both of these useful properties in one material, so I'm going to put my hands together and make an alloy. Iron atoms and iron molecules are larger than carbon. Physicists, please forgive me for describing it this way, but we're on a time crunch here. Basically, an atom of carbon has 6 protons at the nucleus, iron has 26. Bigger. And when we heat up iron, we're causing expansion. And what that can allow to happen is carbon will dissolve and slip in between the iron bits. This is called an interstitial site. When heating iron above 912 degrees Celsius, its crystal structure changes from body-centered cubic to face-centered cubic, austenite. In this form, austenite can dissolve considerably more carbon than ferrite, as much as 2.04% by mass at 1146 Celsius. So, if you want to unravel the mystery of steel, heat is the first step. That's an old reference, but I think it checks out. On an industrial level, if we're talking about scaled-up steel production, we're going to need a lot of equipment. We're going to need a blast furnace, we need iron ore, we need limestone, and some coke. No, not that coke. No, not the other coke either. We're talking about the fuel. Coke is a gray, hard, porous fuel with high carbon content that's made by heating coal or oil in the absence of air for long periods of time. I bet you thought that lump of anthracite I showed you earlier was a non sequitur. Nope, it's all connected. Anyway, coke, along with iron ore and limestone, are layered into the blast furnace, and, as you guess, the heat is turned up. The coke reacts with the blast air to produce carbon monoxide, which then reacts with the iron ore to produce carbon dioxide and metallic iron. Blacksmiths long ago figured out how to do this on a small scale manually by heating iron ore and sprinkling in coal or charcoal dust and then folding the metal over and over again. The act of hammering very hot steel in these deliberate fold patterns will cause physical changes down to the molecular structure. Also, it looks really badass. Blacksmith's so hot right now. Okay, back to the faces of iron. We could do a whole deep dive just on this part of the subject, but the basic idea I want you to hold in your head is that as we add heat and dissolve carbon into the iron, we're going to get different kinds of steel with different hardnesses and different ductility. So we can also add carbon to just the outside of an already made steel object in a process called carburizing. This is used for case hardening. So just the outer layer takes on new hardness properties, but the inside stays softer and more ductile. Because once we have our high and low carbon steels, we're going to want to add other elements to get even more desirable properties. Those elements will be things like chromium and nickel and manganese. In the broadest grouping, we say there are 4 types of steel, and the data I'm going to reference here comes from ASTM International, formerly known as the American Society for Testing and Materials. In order for you, the gifted young engineer, to make educated choices about which steel to use for your application, we have a central authority to grade and categorize. And we've generally agreed that the 4 kinds of steel are carbon, alloy, stainless, and tool. So when we get the blend just right and all those atoms are just vibing, now we have to harden it. Remember when I said earlier that the size of the crystal grain depends on the rate of cooling? It's all coming together. In steel hardening, we're still using heat to push iron crystals through phases, and with the addition of varying amounts of carbon, we're going to have new crystals to play with. But it's not just the heat that matters, it's how you cool the material and how fast that process happens. There are a few processes in place here, namely heating, soaking, quenching, tempering, normalizing, and annealing. Okay, so now that we've made our carbon steel, we're going to gradually heat that steel up and let the heat soak all the way through, just like soaking a sponge. Not actually like soaking a sponge, but the point is we want the steel to have a uniform heat all the way through the sample, or we're going to make some weird inclusions when we go to quench it. An inclusion in mineralogy is anything that forms inside of a crystal that is not actually the crystal. So for example, a rutile that is formed inside of a ruby is an inclusion, and it makes a star ruby. To be clear, inclusions are not always bad. Sometimes we get very cool results. But with steel, we want to be able to control those results. So now we have our hot, evenly heated steel, and we've heated it gradually until it reaches a temperature above the alloy's critical temperature. And then we drop it into a vat of liquid to quench it, to rapidly cool it. That liquid is usually water or oil, although other delicious libations may also be used, things like brine or sodium hydroxide. Delish. Immediately after quenching, the steel will be at that alloy's maximum hardness, and it is also brittle, which means it's also at the moment of maximum danger, and I'm not actually joking this time. The heating and quenching process not only changes the crystals, but it also traps stresses between the crystals. That stress gives the steel extra hardness, just like stress among engineers. That stress can also be released in catastrophic failure, and it happens kind of like a small explosion, just like engineers. Self-care, it's a good idea. A little stress is good, a lot of stress is bad. So to get to a point where the steel is as strong as possible without also being brittle and prone to failure, we have to temper it. There's so many metaphors. Tempering is how we get the useful balance of the hardness and the toughness. The steel is gradually heated until the desired temper colors are drawn, which is generally at a temperature that's a lot lower than the alloy's critical temperature. Different colors in the temper spectrum reflect different balances of hardness to toughness, so different temper levels are appropriate for different applications. The steel is then requenched to fix or to set the temper at the desired level. Normalization may also be called for. Normalizing involves heating the steel followed by a slow cooling to room temperature. The heating and the slow cooling reduces the hardness of the steel and increases the ductility. If you have a very hard steel that you need to work on, you may choose to anneal it. To anneal a material is to heat it above its recrystallization temperature, maintaining that temperature and soaking through, and then letting it cool to room temperature in still air. So if, for example, I've got a big block of hard steel and I only want a little piece of it for a project, I could anneal this, cut off what I want, and then reharden my piece after I finished working it. Okay, so back to crystals for a second. You know ferrite and austenite, may I introduce you to cementite. Cementite is iron carbide with the formula Fe3C and an orthorhombic crystal structure. If you memorize all of these crystal structures, you will be very cool, but to a very small group of nerds. Orthorhombic lattices result from stretching a cubic lattice along two of its orthogonal pairs by different factors, resulting in a rectangular prism with a rectangular base and height. Cementite contains 6.67% carbon by weight, which is pretty high. Cementite mixes with ferrite to form lamellar structures called pearlite and bainite. Cementite has limited use all on its own. It is quite hard, but it's also quite brittle. It gets classified as a ceramic when it exists by itself, but it is also often an inclusion in hardened steels. Pearlite is the name given to a mixture of about 87.5% ferrite, 12.5% cementite. In this form, we have alternate layers of ferrite and cementite, and under a microscope, the surface kind of looks like mother of pearl, hence the name pearlite. 0.3% carbon steel will consist of about 33% pearlite, and the rest is ferrite. The hardness increases with the proportion of pearlite, so hard steels are mixtures of pearlite and cementite. High carbon steels are very important to me, obviously, because I like to smash robots, and my favorite high carbon steels also come with other elements, things like manganese, pushing them toward the alloy group. Now I, of course, am going to talk to you about AR steel, or abrasion-resistant steel. Okay, finally we get to talk about robots. You are so patient, thank you so much. As far as I know, as far as the internet will tell me, in the UK, y'all get Hardox. In the US, we get AR steel. If the trailing number is the same, like Hardox 400 and AR 400, they will have the same hardness on the Brinell scale. So Hardox 400 and AR 400 on the Brinell scale come in about 360 to 440. The actual recipe for the steel varies a lot by manufacturer, and Hardox is a brand name. It's kind of a proprietary blend, like a Sharpie or a Band-Aid. So you've probably heard me talk about Brinell and Rockwell hardness. Brinell and Rockwell are both indentation tests, but they are conducted differently. Do we need both? I don't know. But there is a conversion chart online. If you get a Brinell and you're interested in the Rockwell, you can kind of suss it out. So AR steel, abrasion-resistant steel, is a high-carbon manganese steel, but the sauce is obviously not just in the alloy, but also in the hardening, or I wouldn't be talking so much about hardening. Abrasion-resistant steel is kind of self-explanatory. It's widely used in industry for high-wear applications, things like the teeth of an excavator, rock-crushing equipment. It is also used by various militaries to armor their vehicles, and it's what we use to armor hijinks. You've probably noticed from the photos that hijinks has a monocoque frame, meaning for the most part, the armor is also the frame that supports drive components and electronics. Orion has done tube frame, I have done tube frame, we have both abandoned tube frame, it is for the best. There is, however, a danger in using AR steel for this application. AR is not meant to be a structural steel. It's a different class of steel entirely. And there's a challenge that comes into play the moment you start welding it, which is to say that the heat from welding changes the crystal structure everywhere you're welding it. So you are undoing some of the heat treating process as you weld it. You'll have, at the end, a heat-affected zone that is softer than the base material and usually also softer than the weldment, meaning in combat, that is the area most likely to fail. Another danger in welding AR steel is weld contamination that can cause cracking. But I'm gonna be frank with you. I've seen big burly folks take big dirty stick welders out to the field and do field repairs, so at this point I'm kind of less concerned about weld contamination unless you're in an environment that has like acids. Take it with a grain of salt. Nevertheless, I can tell you that this does work in combat. It works a lot better than, for example, an A36 high carbon structural steel, which was used on the frame for Battle Royale with Cheese, which was pretty well destroyed by Hypershock back in 2018. Funny story? Not funny. I requested AR steel for that robot, but at the time our sponsor could not get it for us. Markets. Meanwhile, the weapon bars on hijinks are all AR 500. So AR 500 comes in between 477 and 550 on the Brinell scale. I made a video a little while ago about our extra stout bar, which is 1.5" thick AR 500. Now we're going to tell you why I don't use tool steel, because the truth is, I used to use S7 tool steel for weapons, and I don't anymore, because I had a bad experience. And that experience was shattering. This is great. I've got Two pieces of broken robot here that are going to illustrate this point for me. This is a piece of Ice Wave's S7 bar, thank you, Mark. This is a piece of Scorpios, thank you, Zach and Diana. So, this is a weapon bar, and S7 is harder than AR500, so if you've got this nice chamfered wedge here, this makes contact at 200 miles an hour with an armor of another robot. This is likely to cut into it. But here's the problem. Can you see that? You can see the wave of energy has gone through this and shattered it. This is called a brittle failure. And it's not just me, but also Ice Wave, Tombstone, Bloodsport. We've all had weapons that had brittle failures in the past. So this is not how I want my weapon to fail. This, meanwhile, this is a piece of Scorpios' front wedge. This is AR500. And this took a big, huge hit. I cut this piece off. I cut it here, and then welded in like a nice flat piece. So we don't want to have bits of, you've got something sticking off of your robot. It's a catch point where another robot could hit you and maybe flip you or rip something off. So this had to go. But here's how the AR failed. Let me get in. It didn't shatter. It kind of ripped. It bent. So there's a little deformation. I'm not sure if you can see, this is blue. Remember we talked about temper colors? Right, so that blue means there was a state change there. That's how hard that hit was. But it didn't crumple. It ripped a little bit and then stopped. So if I'm gonna have a failure on the robot, I want my failure to be deformation, not shattering. Now that's just me. You can do you. You can make all your choices. This didn't lose us a fight. This was just damage. This lost a fight. I think I just cut myself on that. I didn't deburr anything. Okay, so that's my spiel on AR versus S7. But if we're going to talk about hard steels, and I know I want to, we also need to talk about martensite and the stainless group. Martensite is special. I mean, they're all special, but martensite is formed in carbon steels by the rapid cooling of austenite at such a high rate that carbon atoms don't have time to diffuse out of the crystal structure in large enough quantities to form cementite. The carbon atoms become trapped in a somewhat distorted atomic matrix. This is done with really fast cooling through quenching, and the shape is known as a body-centered tetragonal. So stainless steels, the ones that you've seen most often, are usually ferritic or austenitic metal in grades like 304, 316, 430, almost none of which gets used in combat robots, at least not in my robots. But they do get used in medical, marine, and kitchen applications. They are corrosion resistant and very hard. They have a lot of great uses. The stainless group can be further broken down into austenitic, precipitation hardened, martensitic, ferritic, duplex. The exact composition varies from martensitic stainless steel grades, but typically you'll get 15 to 17% chromium, 2 to 2.5% nickel, 0.12 to 0.22% carbon. It may also have small amounts of silicon, molybdenum, and phosphorus. Chromium is the one that's critical to stainless steel. It gives more properties of hardness and toughness and increases resistance to corrosion, especially at high temperatures. And I have a special interest in these because I like to use 17.4 pH stainless steel for weapon shafts on combat robots. 17.4 pH is a precipitation-hardened, martensitic stainless steel. The high chromium content and hardness actually make it really great for machining. Like, it has this buttery smooth surface at the end, which is important in an application like the Hijinks weapon shaft, because we invited several challenges when choosing a live shaft for the weapon core. Basically, the entire shaft needs to be a bearing surface. Now, what do I mean by that? Okay, so at the top of the weapon stack, there is a ball bearing. Its main job is to keep the entire assembly aligned even when we do a big hit. Down at the bottom are long fin bushings and a sleeve between the weapon shaft and the giant block of machined aluminum that we lovingly refer to as the giganut. Use a thin, high-temperature lubricant all the way down. It's applied during assembly every time, and the goal is to make turning that shaft as frictionless as possible. When I say we invited challenges, among them is the moment of inertia for a 68-pound bar, 42 to 48 inches long. It takes a lot of energy to get it moving. And we chose brushless motors because we needed a compact, high-power fit. But the torque at 0 RPM is not great. Ramping up draws less power than the initial start, overcoming that inertia. So what I need from this system is for it to move as freely as possible. I want to be able to breathe on it and get that bar in motion so that we can get it spun up really fast without drawing too much power, damaging the motor controllers. And honestly, it works. We have never had a weapon failure on this robot. I shouldn't have said that out loud. But now's the part where I have to admit that I'm a little bit of a liar, because the thing is, in 2020, I tried very hard to acquire round stock of 17.4pH H900 over 4 inches in diameter that we could cut into weapon shafts. I could not find it at a price that we could afford. Markets. So we made a compromise decision to get the robot built and make the weapon shaft and the drive shafts out of 4140 steel. Thanks to P3D Creations for doing the CNC lathe work on our weapon shafts. I try not to touch these with my bare hands because the oils and acids on your hands you can leave fingerprints that will add texture. I want no texture. So this is the weapon shaft out of hijinks. You got the ball bearing up top. We've got a clamp collar right here, which I mentioned in a previous video. This is the part of the shaft that's embedded inside of the giganut over here. Everything's so big. And these were all CNC lathe cut from a single piece of steel. So it's just gorgeous work. Thank you, P3D Creations. Thank you, IMS. Thank you, Van Bever. Okay, so 4140 steel, what is it? 4140 steel is a chromium molybdenum manganese low alloy steel that is known for its toughness, high fatigue strength, and high torsional strength. So pretty great for drive shafts, I think. I have a hard time saying chromium molybdenum, but fortunately this steel has a trade name. It's called chromoly. And that probably sounds familiar to a few of you now. I still want to acquire some 17.4pH H900 stainless steel for next year because 17.4pH has a higher yield strength. It's almost twice as much as 4140. Right now the material costs about twice as much too. So if anyone would like to sponsor us for season 7, drop a link in the comments because I would love to talk to you. For the drive shafts, I prefer not to use through hardened steel. I like case hardened. I think this is better. You can disagree, but the failure mode of a case hardened steel, it's more likely to bend because the inside's more ductile. A through hardened steel is more likely to shear. If the drive shaft on the robot is going to fail, I would prefer it to bend and then flop around a bit so I can try to stay in the fight, as opposed to shearing, which would leave me without a wheel and probably end the fight for me. I want to fight. So technically speaking, there are other steels on this robot, but those are the main ones that we use. There's one more that I want to show you though. This is the 1095 carbon steel top plate, which we lovingly refer to as the fan service armor. If you have ever unironically suggested using sword steel on a robot, this is for you. 1095 is mostly iron, a little bit of carbon, some sulfur, a little phosphorus, sprinkle of manganese. It is widely popular for knife making, and it has the property of work hardening. So it becomes harder as you hammer it, or also as you drill it or machine it, which can make it kind of a pain in the butt to work with sometimes. So we use this top armor panel with sorbothane to fend off the 500-pound hammer robot Chomp. Bear in mind, this was installed on top of sorbothane on top of our AR armor to make a sandwich. Can you armor your robot entirely in sword steel? Sure, that is a choice you could make, but I'm pretty happy with the choices that we have made so far. And if you are happy with this video, do me a favor, hit the like and subscribe. I'm going to put up more content for you. Ooh, do we have time to talk about hardware? I think we need another video for hardware. Also, I need Orion to do a cameo because this rant about 632 is fantastic. If you like hijinks, follow the robot on social media. We're on Facebook, Instagram, Twitter for some reason. I'm also on Facebook, Twitter, and Instagram, so you can follow me too if you're into this. And next time we'll do hardware. Okay, let's stop here.